Okay, so I will start. So, good afternoon, everyone. I'm very happy to welcome you to this new ArcelorMittal Stelligence webinar. So, today we will talk really about Stelligence because, as you may know, Stelligence is based on a study um, that demonstrates that building with steel and with an intelligent use of the materials can help you to optimize your building and more precisely your office building in terms of environmental impact, of cost, and on social impact. So today we will have Walter, that will be the host of this webinar, and who will present you all the benefits of using steel for your construction. He will be assisted by Neil for the Q&A session that will happen at the end of this presentation. So just, yeah, people are connecting. Hello, everyone. So this webinar is recorded and the recording will be sent to you in the coming days and will be available on YouTube. So you can ask your questions as usual, thanks to the Q&A button at the bottom of your screen, and it will be answered at the end. So I will let the floor to Walter, and thank you everyone for connecting. I hope you will enjoy. Walter, your turn.
Wonderful. Thank you, Justine. Thank you for those words of introduction. Yes, hello everybody, and welcome. So the title of the presentation, Disproving the Myth That Clear Span Construction Costs the Earth. You've probably got an idea of where this presentation is headed. But in the next 30 minutes or so, we basically want to take you through a study that we did, that Justine referred to some years ago now, but it's still a project that's ongoing, and we're looking at different typologies. But this one, as Justine said, is purely focused on the office sector. So the first image, we've got two photographs for you. One of a clear span kind of office block, and the other one of a short span solution to a similar type of building. And hopefully there will be a question which will pop up on your screens. And we really just want to get an idea of what your views are in terms of both cost and the environmental impact. So do you think that the clear span solution is going to cost more? Do you think that the clear span solution will have greater environmental impact? Now, the mischievous people amongst you may want to play a game and really knock us off track, but it'll be good to know what you think. So we'll just give you 1 or 2 minutes to put an answer in there. And Justine might give me a little bit of a nod just to say when those polls have come in.
Yes, I'm just waiting. Okay, it's coming. I will show the results.
Wonderful. Oh, right. Okay, lovely. So we've got some clear span kind of fans out there in terms of cost, which is interesting. So almost a 50-50 split, but clearly a feeling that clear span construction has a greater environmental impact than a short span solution. So wonderful. Thank you very much for those votes. And we'll see whether we can kind of change your view as we go through the presentation. So the next slide. So those two questions that we've just put to you, they indeed were the questions that the R&D team asked themselves. You know, is it possible to have a building with some distinct advantages, but without either the financial impact or the environmental impact? And to go about answering those questions, they basically developed a fictitious office block. And this office block is supposed to be typical of the sort of thing that you would see in Central Europe. So it's a medium-rise building, 8 stories plus the roof, 13.6 meters from facade to facade for daylight penetration. And
Walter,
yeah,
I'm sorry to interrupt. Some people ask you if you can speak a little bit louder.
okay, yeah, I'll try and do that, Justine. Yeah,
Thank
okay.
you.
Thank you for interrupting though.
Sorry.
So here we have an office building which we feel is typical of Central European practice, 13.6 meter span from facade to facade to allow daylight penetration. And with that brief, they then took a look at the way that that sort of building would be built in Central Europe today, and they did that by doing a little bit of market research. And the way that it is built is kind of shown in that diagram on the left hand side there. So what you tend to find in Central Europe is that office blocks are built using quite a lot of precast concrete. Um, those precast concrete solutions, the structure and the services are kept separate. And that tends to force the grid down a particular route. And it sort of hems the design team into one particular solution. The alternative solution, which was looking at kind of what we can do in steel, kind of blurs the boundaries a little bit. So we merge that structure and services zone. And by doing that, it just presents one or two options which aren't available on the left-hand side there. And it opens up the possibility of clear span solutions. So they were the two schemes that they looked at, with that baseline scenario representative of European practice being used as the control and used to measure the ArcelorMittal best-in-class solution scheme against. So you'll hear me talk about best-in-class products and best-in-class solutions. As we've gone through this research project, effectively what we've done is we've looked at the complete portfolio of materials that we have available in ArcelorMittal, and that's everything from reinforcement to organic coating cladding systems to the steel sections and beams that we make. They've looked at all those products, but only brought the ones together that would add benefit either in terms of cost or in terms of environmental impact. So the next step in the process was to basically get a team on board. So the images there kind of show you the people that were involved. So we got some help with developing the design. We got some help with building up bills of quantities, getting costs. We got help with the project planning. But importantly as well, we also had a little group of people shown down there in the bottom left of the slide who basically independently checked what we'd done to ensure that the sorts of conclusions that we were making were valid and relevant, of course. The next step in the process was basically to kind of establish the framework and the metrics that we'd use as the basis of assessment. So 17 indicators were chosen, and they included environmental factors. So they were such things as energy efficiency, consumption of natural resources, end of life scenarios, kind of reuse and recycling benefits. And we also looked at the economic aspects of the build as well. So that involved a life cycle cost assessment kind of before use, but also during the use stages as well. We also looked at speed of construction and the quality of construction. And then in terms of the social factors, we looked at thermal comfort, indoor air quality, acoustical comfort, and design for flexibility, and tried to embody all of that in the assessment of the project, or the two schemes, I should say. So moving on to those two questions, and trying to tackle that first one, can a clear span office really cost less? And of course, the simple answer is, well, yes, we think it can, and that's what the study demonstrated to us. So what sort of things kind of made that possible? Well, it was really all of the work was in the floor zone. That was the key to it. And the element which played a significant part in that was the beams, the Angelina beams, because that allowed us to integrate the structure and the services. So that allowed us to engineer the overall floor zone down slightly. That had a knock-on effect in terms of the total building height, which reduced. And of course, that had an impact in terms of the facade area that we needed, and therefore the facade cost too. So those Angelina beams, basically because of the web penetrations, allowed us to pass services through the beams. But they also created that added value, which is sometimes a difficult thing to put a price on, but it allowed us to be able to eliminate that central column and give something which was much more flexible in use, and would possibly allow a longer design life as well. We also employed a decking product of ours called Kofra Blue 60, and that allowed us to reduce the construction depth of the slab. It's a trapezoidal profile in metal, and it effectively uses less concrete and also less steel compared to some of the decking profiles as well. But you can see from the diagram at the bottom that those two things allowed us to reduce the overall floor zone by 300 millimeters per floor compared to the base case. So when you coupled all those things together, you got the reduction in floor zone, the reduction in facade area, the reduction in overall building height. That led to a reduction in total cost, in construction cost, of 11%. And of course, because of that longer span, you're actually increasing revenue as well, because you've got something which is more marketable on the rental market. I'm just going to sidetrack just ever so briefly and just talk to you about Angelina Beams. So some of you may be familiar with castellated beams. You may be familiar with cellular beams. So the Angelina is a variant of that process, which is kind of particular to ArcelorMittal. Similar process. You've got a one-pass cut. Which is variable. The geometry of the cut is variable. You can engineer that as part of the design process. You separate the two T's after you've cut your parent section in two, flip the bottom T through 180 degrees, and then bring those two T's back together and weld them together. And what you end up with is a beam which is probably 50% greater in depth, and so it's 50% stronger for the same weight of material compared to the parent, and it's probably about 100% stiffer as well. So you're getting you're getting the steel working harder, in very simple terms, with the ability to integrate the services in the case of a floor beam. The openings themselves, as I mentioned before, they can be engineered. So the key thing about any kind of cellular beam is to just have a bit of an understanding about the secondary veer and deal effects around the openings, and to have a rough idea of whether they're going to be significant in terms of the design or not. And generally that relates to the load that is placed on the beam. So if you've got a light load, such as you might have in a roof application, then you find that the veer and deal effects around the openings generally aren't significant. They don't actually dictate the size of the beam. So that means the openings can be more generously sized, and effectively what you do is you maximize that lever arm between the top and the bottom T's, which gives you a much lighter, much stiffer, much stronger section. When it comes to a floor application, your loads have increased roughly by about tenfold. And what that means is that the veer and deal effects, that shearing motion across the cells, they start to become significant in terms of the design. And that has an impact on the geometry that you can choose in the cut. And it generally means that the openings, the shape of those openings, have got to be a little bit more modest. And that's generally the kind of the two things that you need to be aware of. So floor applications, big opening, roof applications, big opening, floor applications, smaller opening to control the veer and deal effects. So that's a very brief introduction to Angelina's. Just a very brief visit at the Kofra Plus. What is it? The Kofra Plus 60 is basically a 60mm metal deck, fairly common profiles in the marketplace. This one is stackable, so it's easy to transport. It also has a trough spacing of about 200mm, so it's a little bit different to some of the things that anybody from the UK might see on the UK market. So it means that if you need to get the shear studs that provide the connection between the beam and the slab working a little bit harder, then sometimes that 200 trough spacing can help you. But in the context of the Stelligent study, the contribution of that deck was actually reducing the volume of concrete required. And obviously, if you reduce volume of material, generally you reduce cost. And if you reduce cost, you'll generally reduce carbon as well. So if we now just take a look at what happens in the ground when you add all of those things together, when we looked at the steel frame, we found that the steel frame of the Stelligent solution, that steel solution, was 70%, 72% lighter than the base case. The floors were 50% lighter, and overall, the building had 34% less mass. So that was a much lighter footprint on the ground, and that translated into both material and cost savings in the foundations. But there are also benefits in terms of speed of construction. So a little bit of a graphic here just to try and illustrate this in very simple terms. But here what we've got on the top left hand side there is the base case building kind of being erected on site with precast elements, and on the bottom we've got our Stelligent's approach using the best in class products. So we're just going to step through that one by one. So the precast columns, they're generally quite heavy, so they'll be to some extent limited by how many you can get on a wagon. So they'll just tend to be a one-story lift, whereas the steel columns, they'll tend to be three-story lifts, so they go up a little bit quicker. The beams in the Stelligent's case, they're a single span, so the pieces, the erection goes up much more quickly. But the big difference really is when you start to drop the floor in, because each of the precast units has to be dropped in separately. And that tends to kind of tie up crane hook time. So what happens is that you see the steel scheme rapidly kind of shoot up on site, and that gives payback in terms of overall program on site. So just to wrap that kind of section of the presentation up, there are some direct cost savings that you make by adopting that approach, and this is what the study showed. So a 13% cost saving in the envelope, 39% cost saving in the foundations, and then a 24% saving in terms of prelims and that type of thing, because the building was basically built 3 months quicker than the base case building. So that essentially means that the client can get a return on his investment much more quickly. So you can get that floor space rented out and get that space starting to generate income. So roughly about a 10% added value impact due to all of those direct impacts on the build of the project. But now moving on and starting to look at the second question, can a clear span office have lower environmental impact? And again, no surprises here. Those two questions we asked at the beginning were rhetorical questions. So again, the answer is yes. It does have lower environmental impact. So how, again, is that possible? Well, again, it comes back to that compactness. So the ability to control the floor zones, and as well as offering a cost saving, you also get a carbon saving or an environmental saving too. So again, just drilling into a little bit of detail here. What did the Angelina Beams do? Well, first of all, they created value by taking out that central column. You've got a more valuable space, but they also contributed directly in terms of carbon reduction. So the Angelinas were designed in high star 460. So that meant that we could get the beams as light as possible, using the least amount of material as possible. But with those holes, we could also maximize the web penetrations to give the maximum amount of space to pass the services or the techniques. The manufacturing process that we use for our steel, the sections that the Angelinas are made from, it's an electric arc furnace process. So you've got a product there with a low embodied carbon. You've also got those benefits in terms of reducing overall building height, reducing the cladding, and that brings kind of secondary carbon savings on the rest of the building. If we move now to the Kofra Blue 60, again, so the sorts of impacts that you saw in terms of cost also actually apply in terms of carbon as well. So you've reduced the amount of material by using that trapezoidal profile rather than a reentrant profile. You've reduced the slab depth, and that all translates into reductions in carbon and a reduction in the overall environmental impact of the building. And then finally, if we started to look at the columns, in the Stelligence alternative, we chose to use high star 460 for the columns. My own personal view is that this should be the default position for most multi-story buildings now, because straight away you get a bit of value creation, because your columns will have a smaller footprint, and therefore you've got greater carpet area. And secondly, you've got the carbon reduction, because a 460 grade column will be lighter than a column in 355 steel. And then compounded with that, you've got the fact that the high star 460 steel is made using the electric arc furnace process, which has a lower carbon footprint also. And for both the Angelinas and the high star columns as well, I'll talk about Xcarb, which is one of the latest offerings from ArcelorMittal, but I'll bring that up at the end of the presentation just to explain what that is. So what did all that mean? Well, if we took those 17 metrics that I started with at the beginning of the presentation and put those into the magic box, effectively what that demonstrated is that the environmental impact of the building was reduced by 16% compared to the base case. If we look at the detail a little bit, if we look at the floors, the difference between the base case and the Stelligence option was a 62% reduction in environmental impact. In the case of the frame, that was 14%. And in the case of the foundations, that was 25%. When you put all that together, those three elements, the three Fs, floors, frame, and foundations, accounted for 75% of the reduction in the environmental impact between the base case building and the Stelligence building. So a lot of the opportunity to reduce environmental impact lies with the structural engineer. Moving on to a softer aspect of impact, so talking about traffic now. Sites, probably as construction professionals, we probably love sites, but we probably wouldn't want to live near one. And this quote and the quote afterwards kind of simply make that point, that as kind of a group of constructional professionals, we should be thinking about the impact of both traffic and noise during the building of the projects that we're involved in. And again, this is where the Stelligence building could offer some benefits in this respect. Ultimately, it comes down to the same thing. The steel frames are lighter. The steel frame solution used less material. So these percentages here are the reductions for the foundations, for the framing, for the floors. So again, you see that it's those three things which have the greatest impact. And they accounted for 71% of the total reduction in mass in the building. So what does that mean? Well, if you've got less materials that need to go to site, that means fewer journeys from the delivery wagons, and that means less dust, less noise, less aggravation to those people local to the building site. So the block on the left-hand side there shows the number of deliveries for the base case scenario. The thing which kind of stood out from that was that it was actually the delivery of the precast units which kind of peaked above the wall line, if you like. And then if you compare that with the deliveries associated with the steel frame, that's kind of where the main differences lied. But the net result was fewer journeys to site with materials, even taking into account the fact that the steel frame had some wet trades associated with the laying of the composite deck. So sticking with the environmental factors, but now picking up on those social elements of that. So if we think about our building, one of the ways that we can regulate the temperature inside the building is by using thermal mass. So that can actually just kind of take out the peaks and troughs of temperature within a building if you use it correctly. And the key to that, of course, is providing access to the thermal mass, and the vehicle for that is usually in the floors. Now, it's about getting the balance right, though. So if you put too much mass in the building, that can actually have a negative effect, and it can actually start to lock in heat, which is then quite difficult to get out of the building. So research has essentially shown that the optimum slab thickness for a diurnal cycle, so a 24-hour cycle, is basically 75 to 100 millimeters. If you combine that with nighttime purging, so where you open the windows, you allow the cool air in, then during that nighttime period of about 8 hours, 6 to 8 hours, that's enough to allow the heat to be purged from within the slab that's being locked up during the day. And if you combine that with shading techniques and reduce the solar gain, then you can get that working to create the right sort of environment within the building. But the key thing is getting the amount of mass right. And with the steel solutions, whether it's a Kofra Blue 60, so a shallow decking profile, or a deeper decking profile, you've roughly got the right amount of mass to give you the best performance. So or coming up to the last few slides. So this is just talking about our best in class products and starting to look at where they can benefit you in terms of sustainability ratings or picking up points in terms of BREEAM and LEED. So again, when we assessed our products, we basically only chose best in class products which could add value in terms of those environmental assessments. And in terms of BREEAM, basically by that collection of products that we used in the building, we added 3 credits. So the rating of the scheme went from very good to excellent in terms of the Stelligen scheme. And then in terms of LEED, it went from gold to platinum. The key to it all, though, was essentially the fact that we could support all of the products that were specified in that steel building with EPD. So you have all the environmental impacts associated with all of the materials that went into that building. So a lot of knowledge, if you like, a lot of detail about the caliber of the buildings, of the products that you're putting in the building. And finally, on to a third question, which we didn't actually ask, but how can we kind of make this building kind of part of the community? How can we get people to like being around the building, like being inside the building? And a lot of that is really to do with the huge palette of colours and textures that we can offer from our cladding materials, our organic coated materials. So we've got things like granite, HD Extreme, which is a pre-painted steel, a 3-coat system, which can give you, well, we can guarantee it for 40 years. I think that's in a C2 environment, C2, C3. So that probably means that it's getting close in reality to being on the building for the full design life of the building, which is quite impressive. And then if you're looking for different textures, we have things like eclectic, which are a little bit less mainstream compared to your regular profiled cladding. And then we've got offerings like Muralis, which basically again is a coated product, but where you as the designer can actually choose the pattern that goes onto the cladding. And then this just shows some of the buildings where we've used some of those products, and I won't go through them in any great depth, but I will just labour on that photograph shown down at the bottom left. So the interest here is you might see in that photograph on the right hand side a blast furnace, and that indeed is one of the blast furnaces that used to operate at our sites in Belval and Differdange. But they've actually been shut down for about 30 years now. They're only there as a little bit of a museum piece, a bit of industrial architecture. And the reason why that colour was shown on the building to the left-hand side was to reflect, if you like, that steel heritage. But this site now in Esch is basically an electric arc furnace site where we produce our sections and our high star sections and our sheet piling. So just to kind of conclude, I think I may have one slide after this one. So this is kind of bringing all of those benefits together and try to attach a value to them. The direct value was very easy, but actually when you look at the indirect value, we now have to pay for emissions to atmosphere in terms of carbon. So actually if you can save carbon emissions, then you're actually saving money also. If you look at the rental value, that open span means that you can command greater rental values. And all of those things basically totted up essentially meant that the assessment was that Stelligen's approach to that building added 20% in added value to the overall scheme. So what I've actually done in that presentation is basically taking you through the 10 key benefits that were identified as part of that research program from ArcelorMittal's R&D department. So they were compactness, flexibility. We learned about the benefits in terms of environmental impact, the speed of construction, reduction site traffic, better BREEAM ratings, and ultimately a better value offering. And then I wanted just to end the presentation with an offering that we've brought to market quite recently. And this is really in direct response to the climate emergency and this increasing need that we have to design out embodied carbon in our structures. So this is the way that ArcelorMittal are trying to play a part in that debate. And the Xcarb offering basically has three components to it. If I start in the top right, we've got Xcarb, recycled and renewably produced. So we produce steel in two ways, principally. We produce electric arc furnace products, and the Xcarb recycled and renewably produced basically addresses those products that come from the electric arc furnace. And we've simply asked ourselves, how can we reduce the embodied carbon in those products? Now, they're already quite low in terms of embodied carbon, but the principal thing that we can do, and we can do it relatively quickly, is by tying that electric arc furnace into a source of renewable energy. And by doing that, if there's demand for more of this product, that puts demand onto our energy suppliers to increase the rate at which they decarbonize. So that's what recycled and renewably produced is about. It's an offering which is basically tying the electric arc furnace into a decarbonized electricity grid. If I go diagonally down to the bottom, we've got Xcarb green steel certificates that applies to our blast furnace products. This one's a little bit more trickier for us, but for the last 18 months, we've rolled out a series of reduction measures at our blast furnaces in Europe. And the net effect of that is that we've saved round about 250,000 tons of carbon to atmosphere. And we've translated that into an offering of zero carbon product. So what we can offer is approximately 120,000 tons of zero carbon steel that comes from the blast furnaces. So that could be organic coated steels that you'd use for the cladding on a beam, on a building, or it could be metallic coated that you'd use for your decking products, or it could be plate that you might use to make a plate girder. So that's what that is, and what we do is we offer a certificate when you purchase that material, and the reductions that we've made have been certified and validated by a company called DNV to ensure that the accounting of those carbon reductions is correct. Next year, the volume of material that we'll be able to offer will increase to 600,000 tons. And that's because next year we'll be opening or commissioning our plant in Ghent, which basically uses two processes to reduce the emissions to atmosphere. One of those processes actually by displacing fossil coal or pulverized coal in the blast furnace with a circular form of carbon in the form of wood waste. So we take wood waste, treat it, inject that into the blast furnace, that displaces fossilized coal, and then combined with that, we're actually capturing the top gases off the blast furnace, capturing the carbon monoxide, and we're actually able to use that to produce bioethanol. And that allows us to reduce our emissions to atmosphere. Tying those two things together, we want to do more as a company. We want to accelerate more quickly and decarbonize our business more quickly. And to facilitate that, we've created an innovation fund. And into that innovation fund, we're putting $100 million, I think it is, per year. And the idea is any companies who are involved in either researching or setting up startup businesses that will accelerate the rate of decarbonisation of the steel industry, we're interested in hearing from you, and it may be that we may be able to support those developments. So that is kind of Xcarb in a nutshell, and that brings me to the end of the presentation. So I'm going to thank you for your attention, and hopefully I'm going to introduce Neil into the conversation, and Neil will let me know whether there's been any questions cropped up as we've gone through the presentation. So we'd love to hear your questions.
Thank you, Walter. I take it you can hear me.
Yeah,
Just to check.
Okay.
Yeah, we've had one question. Could you just in the study with the Angelina beams, could you just explain the primary secondary beam relationship and the spanning of the decking? What was the 8.1 meters maintained that was in the original baseline building?
No, so the central column was taken out, and the beams were spanned the full width of the building, which I think was 13 and a bit meters. And the arrangement of the beams would be what we describe as a clear span secondary arrangement. So the beams would have been at approximately 3 meter centers, and the grid would have been, approximately 6 meters, with the decking spanning in between. So those beams were designed as secondary beams.
Long-span secondary, yeah. Okay. Second question. The question is asked about Angelina beams, but I think it really relates to any composite beam. Can the Angelina beams be detailed for demountability?
In principle, yes. There's an excellent publication from the SCI which looks at creating a composite solution that where the slab can be decoupled from the beam at the end of life, so you get the benefits of composite action, but instead of having a through deck stud welded arrangement, you essentially use an M20 bolt, which is basically bolted to the flange. And there's a couple of extra details that you need to take care of, but essentially it allows that building to be decoupled end of life, for the Angelinas to be reused, and also for the slab to be reused. So sorry, I should say SCI is the Steel Construction Institute, so a research and academic body in the UK.
And I guess one of the interesting questions, an obvious question you might say, just to talk about acoustic performance, and I guess floor vibration, possibly also add into this concerns or questions there might be about deflection on long spans. Okay.
So in simple terms, all of those problems have kind of been, they're not problems, they're perceived, sometimes perceived as problems, but they're actually things that can be engineered out. So in terms of acoustics, particularly in terms of office buildings, the depth of concrete above the deck is sufficient to prevent airborne transmission of sound. And then it depends obviously in terms of what you do on top of the slab in terms of limiting kind of impact transmission. But usually in an office building, you've got a raised floor, and that raised floor basically kind of takes out the impact that you get from footfall force. So acoustics not really an issue. And there are many buildings that have been built in this way in the UK, and they really don't manifest themselves as problems.
What if you were going to go to vibration sensitive buildings like hospitals and things like that?
Yeah, so vibration sensitive buildings, so we need to sort of separate a little bit out acoustics with vibration. So if we go to acoustics, there are ways and means. We've used this form of construction in residential buildings in the UK, and it is really just a case of using appropriate details, and we have a library of details that we could kind of refer to you to overcome those issues. If we talk about the issue of vibration, again, it's just applying the engineering. It's a very simple equation that you use. It's Newton's second law. And essentially, when you consider vibration, what we're concerned about is accelerations. So it's really just about engineering the mass that's in the system. Sometimes when you look at long spans, the general reaction from an engineer is that they will be more sensitive to vibration. And in one sense they are, in the sense that the frequency of a long span beam will generally be less than for a short span beam. But actually when that beam moves, when people traffic it, it actually pulls in more mass from the floor. And that mass actually helps to control the vibration. So again, I can talk about projects that have been done in Paris, 17-meter spans, vibration measured on site. This was done a number of years ago and shown to be adequate. And there is a multitude of buildings that have been built in the UK, tested, and vibration isn't a problem as long as you deal with it at the design stage. And those spans in the UK, 15 meters, 16 meters, 17 meters, quite common.
Okay, I'll take. We've had a question about infills for Angelina Beams.
Yeah, I think with any cellular beam that you make from section using an expansion process, you try to eliminate infills wherever possible, because if you have infills, they carry a labour cost and they can add cost unnecessarily. But essentially, it's a profiled shaped plate that we'd use, and they'd be fitted much in the same way that you would do for a regular cellular beam. So it's a fitted plate that's then welded into the opening.
Yeah, okay. Question about dry processes and whether or not the concrete topping can be avoided. I guess this is maybe looking at precast. Obviously, there would be concrete with metal decking.
Yeah, I mean, the metal decking process, it is a wet trade. So there isn't really a way that you can get away from that unless you try and take the process off site. I guess all I can say really is that it probably depends where you are geographically, but certainly in the UK, that practice is quite common, quite efficient in terms of an on-site process. But you know, we have done schemes which involve a cellular form of construction with precast units. So that is a possibility. Obviously, if you're going to add a screed, you then say, well, you know, why bother? But it is possible to eliminate wet trades, but probably using a slightly different form of construction.
And then finally, this is just this question hasn't been asked, but I'll sort of ask it if I may. Just the general feeling about when you're talking about climate emergency, and you're talking about long span versus short span, and the application of engineering judgment. We see in some instances that when people are talking about embodied carbon and sustainability, their decision making becomes very binary. And I just wondered if you had a comment about how engineering judgment can allow you to approach some of the issues engineers face when dealing with these topics.
Yeah, it's an interesting question, that one, Neil, isn't it? So really, what you're talking about is value, and I guess in some respects, carbon value. It's interesting if we eliminate concrete and we assume that we had a short span steel solution compared to a long span steel solution, then my estimate would be that you'd increase the steel content of the long span solution by about 10 kilograms of 10 kilograms per meter squared. I think would be fairly typical. Now, of course, that has an impact, and you can't deny that. If you went to short span, you'd probably save that 10 kilograms per meter squared. But if you actually quantify that impact, then using our products in particular, the actual increase in carbon content would be around about 5 kilograms of CO2 per square meter. And if you compare that to a total building requirement by the likes of Letty in the UK, which sits at 600, to me that is a relatively modest increase for a lot of value in terms of the flexibility that you get with a clear span solution, value in terms of the adaptability, and value, we hope, in terms of longevity. You know, so if that 5 kilograms of CO2 per meter squared allows you to get another 10, 15, 20 years out of the building, then to me that's worth having. And I think that is the value I think that we're going to have to make as professionals. I don't think it's a simple solution of just saying, right, we're going to go for the lowest carbon possible. Yes, we've got to get the carbon down, but we haven't got to severely impact the functionality of the buildings that we're designing.
And I think this will be the final question, just a request for where you might find design assistance for Angelina Beams and Kofra Plus decking. Yeah.
So at ArcelorMittal, we essentially have a design service. So we have a bunch of engineers who sit well actually around the globe, around Europe, but also headquartered in Luxembourg. We also have software which is freely available. So if it was something that you wanted to investigate, we can certainly support you with that. The software is written to the Eurocode. Obviously, you'd have to apply your own country national annex, but it's there and it's available. And the same applies to the Confloor decking too.
Okay, that's great. We have no further questions on the Q&A.
So that's wonderful. Shall I close then, Neil, or do you want to close?
I think you should.
Yeah, wonderful. So just Neil, thank you for fielding those questions. Justine, thank you for your introduction and your support to pull this presentation together. And thank you to everyone on the call for listening. And thank you in particular for your questions. Really appreciate those. I think a recording's been made and that will be posted on the Stelligence website shortly after the presentation. And if you do need to get in touch with myself, Neil or Justine, then please do so on the email address below, the stelligence.arcelormittal.com. So thank you all and enjoy the rest of your day.